Hello everyone. I'm going to set up two membranes and make them interact with each other. Here I have my templates, one with comments, one without comments. If you don't know how to create or generate a template, please watch the corresponding video. Now what I have here is a very simple configuration file. The project name is membrane collisions and it has a 2 mems subfolder. The simulation duration is set up for 400 picoseconds and we have one membrane class which uses this particular mesh. The spring coefficient is 1, bending coefficient 50, and we've scaled it up to 100, and there's an interaction table M0 here. So what I'm going to do now is I'm just going to run this configuration file. It was called mem collision text and the platform ID for the OpenCL is 2, and since I only have one GPU, the default platform device ID, which I can ignore but I'm just going to write anyway, would be 0. Okay, I don't understand ecosphere mesh file. Let's see what's wrong. Oh, right you are. Sorry, I'm going to edit this line. That's better. I messed up the directory of the mesh file. I'm going to run it again. Is not a membrane parameter. Right you are again. We need a mesh file here. If I'm wrong, let's consult with the template. What do we need? Mesh file has a capital F. Okay, F. Everything should run now. Yes. Okay, I'll fast forward this bit. Okay, so I'm going to open a new tab, VMD and results. Let's just change directory to the project cd results mem collision 2 mems. Yep. Okay, so VMD and the PSF file together with the XYZ file. Okay, fair enough. This is a membrane that's just wobbling in space. Now we're going to introduce his new buddy. Okay, how do we do that? Very simple. I'm just going to define another membrane class and I'm going to use the same mesh. I'm going to use the same spring coefficient, the same bending property and the same scale. So it's a hassle to write everything and duplicate it. So I'll just name this membrane membrane A, and I tell this one, which is membrane B, to copy everything from membrane A. But they can't occupy the same space. Well, they can because they don't interact. But I'm just going to shift one of them to the side. And how we do that is that we have a coordinate translator vector, which I'm going to place here. And I'm going to put it 250 units in the X direction. Save it, run it. Okay, since I have only one GPU, it doesn't really matter to define the platform device ID. What's wrong? Number of interaction table. All right. Okay, so now we have two classes and we have to redefine the interaction table. So here's how the interaction table works. I'm going to, let's just rename it. It's not important, but I'm going to name it MA for membrane A, MB for membrane B. And I don't want any interactions whatsoever between them. Okay, so here's how the interaction table works. Okay, so let's say that we have a configuration file that has two membranes, membrane 1 and membrane 2. Okay, you can think of the interaction table as an interaction matrix. Okay, so in an interaction matrix, here, this square defines how membrane 1 interacts with membrane 1. That is, how membrane 1 interacts with itself. This square will define how membrane 2 will interact with membrane 1, and this square will tell us how membrane 2 will interact with itself. Naturally, this is a symmetrical matrix, so it doesn't really make a difference. Whatever it's in this square will be in this square as well. So the only thing we need, the minimum information we need to define interaction between all classes are these 3 squares. Now, if I have a larger configuration file that consists of 2 membranes, 2 actins, 2 ECMs, and 2 chromatins, that is 8 classes in total, I would need to write a larger interaction table that is 8 units along each edge, and this diagonal will define how the classes will interact with themselves. We don't need all the matrix, we just need half of it, which are these white squares. And each of these will tell VCM how the classes can interact. Okay, now let's get back to the configuration file. So I have 2 membranes, MA and MB. Now this 0 is the same as this square, so it tells me how membrane 1, membrane A, interacts with itself. This is this square, so how membrane B interacts with membrane A. Okay, so I've set all the interactions to 0. That means these will not interact with each other at all. Now I will run the simulation again, and I will fast forward to the end of the run. Okay, I'm going to interrupt the simulation because we don't really need the results for this one. We just want to see 2 membranes next to each other. So VMD, what do we have now? We've got another one at a later time, PSF, and which one? The later time, XYZ. Okay, so here we are, 2 membranes sitting idly by. Now I'm going to make them crawl towards each other. Well, not so crawl, but to just move towards each other. Okay, let's define a velocity shift vector, and let's say membrane A goes to the right with speed 1 and membrane B goes to the left with speed -1. I'm going to run this thing again. Okay, done. Now let's see what this is. Now I'm going to show you a preview of the project folder. So this is the 3rd run we have done. So VMD, the last one is at 45 PSF, and another one XYZ. Okay, so let's rewind. Now what happens is that these 2 membranes move towards each other, but they're not interacting with each other, so they just pass through each other. So what sort of interactions can I define? I'm going to go to the end of the configuration generator, and here there's a short explanation of this interaction table that might help, and I hope it helps. And the some interactions here. One is the WCA, which is the Weeks-Chandler-Andersen potential. I'm going to make use of that. I'm going to tell membrane B to interact via the Weeks-Chandler-Andersen potential with membrane A. I'm going to save it and run it again. Very well, finished. Let's take a look at what we have now. So at 48 PSF, 8 X, Y, Z. Okay, let's go to the beginning of the simulation. Now we have two membranes that repel each other via the Weeks-Chandler-Andersen interaction. Now I'm going to make them stick to each other. Okay, so I'm going to quit this, and we have this Lennard Jones potential here with the LJ symbol. I'm just going to replace the WCA with Lennard Jones, and I'm going to run another one. Okay, done. Let's see the results. 58. Okay, let's rewind. I'm going to make this bigger because this should be interesting. I'm going to play it. Now they move towards each other, but it's elastic. They stick to each other and display some interesting physics. Okay, so now you can do this with any class. There could be a membrane, chromatin, actin, whatever, and you can define these potentials between them. Now I'm going to do something else. I'm going to make one of these smaller, scale it to, let's say, 70, and I'm not going to move it. I'm just going to put it inside the other one, and I'm going to make them repel each other. One thing about the Lennard Jones potential. Now, I didn't define the depth. So the depth of the Lennard Jones potential by default is set to the temperature of the system, which is, let's generate another template. My temp, no comments. I want to overwrite it, and I don't want any comments. Where I am, my temp, no comments. Okay, so the default value of the Lennard Jones epsilon is the temperature of the system defined by KBT. Now you can put in a custom value. That way the epsilon of the Lennard Jones potential between two classes will be defined. I have it somewhere here. Let's see. Okay, yes. If you have two classes and you define two different Lennard Jones epsilons for them, when they interact with each other, they will interact with an epsilon that is the geometrical average of those two values. That means the square root of the multiple of those values. Same goes with the Lennard Jones sigma, which is by default the radius of the nodes of the class, if you define a custom radius, or the radius of the two classes differ, the sigma of the Lennard Jones will be the average of those, will be the sum of those sigmas. Let's see if this is finished. Yes. And now I'm going to take a look. Okay. PSF. So two of them inside each other and they repel each other. Let's see how that looks. They just bounce off each other. Now you can play around with this and change all sorts of settings. Have fun.